This video goes over example problems in dynamics, strictly one-dimensional. For those of you who are more interested in using Maple, these are good example problems of using DSolve. Let's get started. In this first problem, we have a very dense ball in a thick liquid. Obviously, the earth is pulling down on the ball. However, since the ball is in the liquid, there is a buoyancy effect from the fluid and the fact that because the ball is falling, there is a drag force on it. We know some information about it, and we're interested in particularly figuring out the drag constant on the ball as it falls. This is a classic case of a momentum principle situation. The motion of the ball, it depends upon all the forces on it. That motion therefore affects its position with time. So the momentum principle is, as Newton wrote it, the rate of change of momentum of the object is equal to the net force on the object. In this case, the net force is that of the earth and the fluid, where the force of the earth is downward, m times g, and the force of the fluid is due to the buoyancy effect, i.e. the mass of the fluid displaced, plus this drag coefficient, which is in the opposite direction of its traveling. The mass of the fluid is equal to the density of fluid times the volume of the fluid that is displaced. And everything looks good, except in this derivation, I'm using momentum as a function of time, not velocity. Therefore, wherever I see velocity, I must replace it with momentum divided by mass. Since we have two rate equations, we need two initial conditions to find a single solution and not a family of solutions. The momentum of the ball initially is 0 because we're dropping it, and the height of the ball is at some distance h. Consequently, we are ready to DSolve. We have one rate equation, a second rate equation, and two initial conditions. This allows us to get the solution for both the position as a function of time and the momentum as a function of time in terms of the constants provided. How do we extract out the solution? Well, we can evaluate the solution from our set of solutions, and if necessary, we can make a function out of it, which is a function of t. At this point, our goal was to find, given the fact it falls for a time t and hits the bottom, what is the drag coefficient? Unfortunately, this is too complex to find a closed form solution. And thus what we have to do is solve it numerically with the values that are provided. Notice each constant is assigned a value in MKS units. Now I can use Maple to solve for the floating point value for when it hits the ground, what is the value of C sub d. Notice I've given C sub d a range for it to look for to make sure that it only extracts a positive value. If we define our drag coefficient as the solution, we can reaffirm that when the ball reaches the ground, i.e. when y is equal to 0, the time is the 5 seconds given. This allows us to plot the height of the ball as a function of time starting at h and eventually getting to the bottom of the well, and its momentum with time. Initially, it's going faster and faster in the negative direction, but eventually reaches what is sort of a terminal momentum. This terminal momentum of the magnitude of the ball is a consequence of the fact that the drag force, which is pointing outwards, increases as the ball gets faster and faster. The second problem is somewhat like the first problem, except we're going to A, throw the ball up through a fluid, and B, we're going to say that the drag force of the fluid, in this case air, is proportional to the speed squared. And notice it is in the negative direction. So the drag force is both up or down depending upon the velocity of the ball. The layout of the physics is the same. It is a dynamics problem involving momentum, and the momentum is affecting the position. The net force on the ball is that due to the earth and that due to the air. The force of the earth is in the negative direction and is equal to mg. And the force of the air is going to be strictly the drag force. We can ignore the buoyancy force since it is so small. Here is the velocity term, momentum over mass squared, and you notice it has to be pointing in the negative direction of the direction of motion of the ball. This direction is defined by p hat, and the direction vector is the vector itself divided by its magnitude. As before, we must give it initial conditions. We'll say that the ball has some mass m, the mass of baseball, and is thrown up with its initial velocity v0. And its initial height is height h. the height of the observational deck on the Empire State Building. Can Maple find a closed form solution to the position as a function of time and the momentum as a function of time, given these two equations and the initial conditions? And the answer is it's not a smooth situation and it involves an integral. Hence, it is best to try to solve this problem numerically. To solve the problem numerically, we must provide numerical values for all the constants. At this point, it is useful to look at the four equations to make sure that all constants have been defined. And now the Maple code. We are going to desolve this problem. Again, the two equations and the two initial conditions stored here, but numerically, and it's best to provide the output in as a list procedure. The solutions are found in these procedures, which we can extract out as functions. And now we can actually solve the problem. For example, when P of t is equal to 0, that's when the ball has reached its highest altitude. At that point, we can say the position at that time up is the maximum height. This turns out to be about 440 meters after about 3.3 seconds. Next, we can find the total time that it's in the air. That means the time when it reaches the ground. And from that, determine its maximum speed just before it hits the ground, which means the momentum just before it hits the ground divided by mass. This turns out to be about 60.5 seconds, and it's a speed of 42.5 meters per second. Now we can plot the position as a function of time from 0 to when it hits the ground, and it looks something like this. And we can plot the momentum divided by mass, i.e. the velocity as a function of time, from again, when we throw the ball up in the air to when it reaches the top of its height to when it's just about to hit the ground. At some point, it reaches a terminal speed. This is when the drag force essentially is equaling the weight of the ball. At that point, there is no net force on the ball, and therefore the momentum of the ball is not changing, nor is its velocity. Given that Maple defaults to setting animation at about 10 frames per second, if we want to plot this in real time, it turns out we need about 166 frames. So now we can animate the plot, which consists of a point for which there's only one point at 0, y, using n frames of frames. Click on it, we push play, and this is, in real time, the flight of the ball if we throw it straight up at nearly 100 miles per hour until it hits the ground. Even though these are somewhat complex physics problems, the amount of Maple used is quite small. You must be able to assign an equation. You must understand what an equivalence is. You must be able to use desolve. You must be able to extract the solutions either symbolically or numerically. And it is useful to know about fsolve to solve for specific values in your problems. I have included a link to a more complicated type of trajectory problem, this one involving stratospheric jumping.